In machine learning, a model that performs flawlessly is rarely a success. When an algorithm achieves absolute mathematical perfection on its training data, it is usually a symptom of structural failure. The system hasn't mastered the underlying logic, it has simply memorized the answers, and when exposed to the real world, it collapses. To see how this happens, we measure what is called model capacity, using polynomial regression as our test case. Capacity dictates exactly how much flexibility an algorithm has to bend and twist its predictions. This chart's top left shows a rigid linear model failing to capture the data's true curve. Increased to a degree 3 polynomial, it gracefully tracks the underlying shape. But at degree 9, the line contorts wildly to touch every point, completely losing any rational shape. This degree 9 model has excessive degrees of freedom. It possesses so much capacity that it has stopped learning the actual signal and has started mathematically memorizing the random noise inherent in the data points. This exposes a critical distinction. There is training error, which is the error measured strictly on the data we already have, and there is true expected error, which is how the model will perform on instances it has never seen before. Relying solely on training error is dangerous. Because it overfit the noise so perfectly, the degree 9 model will falsely appear mathematically superior to the simpler models on a testing sheet. Because training error is a deceptive metric, evaluating a model requires a method to empirically expose its true expected error and a mathematical mechanism to force it to stay simple. If we cannot trust our training error, we face an operational challenge. We need a way to safely test the model's predictive power without requiring an infinite supply of new data. The solution is leave-one-out cross-validation, a procedure that simulates unseen data by strictly rationing the data we already possess. Imagine a set of 10 data points. The procedure begins by isolating one point strictly for testing, marking it as the validation set. The algorithm then uses the remaining 9 blue points to train the model. The process then repeats. It rotates that isolated testing point through all 10 positions, generating 10 different iterations. By averaging the errors from predicting those 10 hidden points, we extract an unbiased estimate of the model's true performance. This chart shows the results of cross-validation applied to our polynomial models. As the polynomial degree increases along the x-axis, the blue line representing training error crummets towards 0. The model thinks it is improving. But when we overlay the validation error in red, a dramatic U-shaped curve emerges. It initially drops alongside the training error, bottoms out at degree 2, and then violently spikes upward. The data shows the mathematical extreme. At degree 9, the training error is exactly 0, yet the validation error explodes to nearly 6,100. The model is completely broken. Cross-validation definitively proves exactly when the model breaks. Knowing this, the next step is to analytically integrate a complexity penalty directly into the math to prevent it from reaching that point. We need to mathematically punish the model for using large, complex weights to fit the data. We do this through regularization. This involves appending a specific penalty term directly to the standard error function that the algorithm is trying to minimize. In L2, or ridge regularization, the math works by calculating the standard sum squared error, and then it adds the sum of the squared weights to the loss calculation. Large weights now incur a heavy mathematical cost. We can translate this algebra into geometry. Think of the error function as a 2D topographical map, a set of elliptical contour lines forming a valley that the algorithm is trying to descend to find the lowest possible error. Because of that squared penalty term, the model is trapped inside a rigid circular boundary. It is geographically prevented from reaching the absolute bottom of the error valley, where the overfitted extreme weights live.
The mechanism driving this is constrained optimization via Lagrange multipliers. The model settles at the exact geometric coordinate, where the outward push of the error gradient perfectly opposes the inward pull of the circular boundary. The vectors lock head-to-head. The size of that circular boundary is controlled by a single dial, the regularization coefficient, lambda. If lambda is set to 0, there is no boundary, and the model overfits freely. If lambda approaches infinity, the boundary crushes the weights down to absolutely 0, leaving a flat line. L2 regularization successfully restricts model capacity. It mathematically forces a strict compromise between perfectly fitting the training data and keeping the physical parameters small. If we change that mathematical penalty slightly, bounding the absolute values of the weights instead of their squares, how does it alter the model's architecture? This substitution is called L1 regularization, or Lasso. Bounding the sum of absolute values changes the geometry of the constraint. Compare the shapes side by side. The squared terms of L2 create a smooth circle, but the absolute values of L1 create a sharp, angled diamond. Watch what happens when the elliptical error contours expand outward to meet these two different boundaries. On the left, the L2 contour intersects the smooth circle at an arbitrary point along its curve, floating somewhere between the x and y axes. Both weights are reduced, but neither is exactly zero. But look at the L1 diamond. Because of its sharp corners protruding directly onto the axes, the expanding error contour almost always hits a corner exactly. Landing on that corner produces a specific mathematical result. It sets one of the weight parameters to exactly 0. This chart shows real-world data reflecting this geometric reality. As the shrinkage factor increases, the lines representing different input features hit the 0 axis and flatline completely. Irrelevant features are systematically deleted. This geometric preference creates sparsity. Lasso performs active feature selection, surgically dropping irrelevant inputs from the model rather than just shrinking them toward 0. Seemingly minor changes in mathematical syntax, squaring a number versus taking its absolute value, dictate the physical architecture of the resulting machine learning model. We have seen that L1 and L2 force a model to be simpler, but to understand why this leads to better predictions, we must deconstruct the total error into its constituent components. By applying the variance lemma, we can separate the total expected error into 3 distinct categories, revealing the underlying tension that defines every estimator. This lemma separates the error into 3 base elements: the inherent dataset noise, the squared bias, and the hypothesis variance. Noise is the irreducible baseline error. No model can fix this because the real-world data being measured is inherently messy. Variance represents the model's hypersensitivity to that specific noise in its training sample. This is the chaotic degree 9 polynomial, violently reacting to every random variation it sees. Bias is the systematic error caused by a model's inflexibility, like the rigid linear model that lacks the parameters to track the true curve of the data. Our regularization dial, the slider for lambda, mathematically links bias and variance. At 0, the model has low bias, but suffers from massive variance. As we increase lambda, we intentionally force bias into the system, crushing variance down to a stable level, minimizing total error. Regularization is the deliberate choice to make a model mathematically dumber on the training set. By adding bias, we prevent it from memorizing the noise, so it performs smarter on unseen data. Building robust machine learning models is not the pursuit of 0 error on a training sheet. It is the rigorous geometric calibration of the tension between a model's capacity to learn and its ability to generalize.